Okay, so this will be the second lecture on Diene chemistry. And just to recap, we saw that dienes can undergo polar addition. Essentially what happens in those reactions is the diene reacts with HCl and generates a resonance stabilized carbocation. Chloride is able to attack the species to give rise to two products. There is the simple addition product, where the chloride attacks carbon number 2, and then there is the conjugate addition product, where the chloride attacks carbon number 4. Right, so my 1,2 product, my 1,4 product. We also saw that because this carbon is secondary, it bears a larger fraction of the positive charge than does this carbon. So in reality, I can write a delta plus 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 at this carbon, and I guess a delta plus of that carbon. So that means that attack by chloride at carbon number 2 is more facile than attack at carbon number 4. And we translate the facility, or the greater facility of that reaction, into a reaction profile diagram in which we have a small energy barrier leading to the 1,2 species, but a large energy barrier leading to the 1,4 species. So here would be my ion pair, right? This is my carbocation and my chloride. This would be my 1,2 product. This would be my 1,4 product. And attack to give the 1,2 species is easier. In other words, I've got a lower energy barrier. Attack to give the C4 product is more difficult because the carbon is less positive, and so that's going to give rise to the higher energy barrier. Independent of that is the fact that the 1,2 product, being a monosubstituted alkene, having only one alkyl group, is a less stable species, whereas the 1,2 product, the 1,4 product, is actually more stable. So we saw that this was a case of kinetic versus thermodynamic control of a reaction, in which the more stable species forms more slowly. So this is the more stable species, and it's formed by the more difficult pathway. And this is counter to our previous experience. Typically we find that the more stable entity forms faster in obedience to the Hammond-Leffler postulate, but not in this case. In this case, in these unique cases where there is kinetic versus thermodynamic control of a reaction, the more stable species forms by the more difficult reaction. But if you remember, we started this discussion about kinetic versus thermodynamic control to answer the question, which of these two compounds do we form? Do we form them both? And if we do, what are the relative yields? Can I control my reaction conditions? Can I doctor my conditions to get largely one species or to get a preponderance of another? Well, the reaction profile diagram gives us an indication as to how we might engineer a successful reaction to make both the 1,2, or to make either the 1,2 or the 1,4 as the major product. And here's how it works. Let's say we run the reaction at a low temperature. Well, a low temperature limits how much energy is in the system. And so at a low temperature, my system will probably have enough energy to jump this barrier, but it probably won't have enough energy to jump this one, right? Because that's a higher energy barrier. Now, there will be a few molecules in the system that will acquire enough energy by collisional activation to jump this energy barrier leading to the 1,4 product. So I will get a small amount of the 1,4, but I'm going to get a large amount of the 1,2 because most of the molecules in the system are energetic enough to jump this small barrier. There might be a small fraction of my molecules which have gone into the 1,2 product which can jump back, right? So what I'm going to find is that there are 3 pathways that are operational. The major thing happening would be going from the ion pair into the 1,2 product. That's the major pathway. I would probably get a trickle of the 1,2 species to reform the ion pair, and just a trickle of the ion pairs forming the 1,4 product. So if I run my reaction at a low temperature, and really for a short time, right, for short exposure, I will get a large amount of the 1,2 product. Now, why a short exposure? I want a short exposure because I don't want my molecules to acquire enough energy, as I said, from collisional activation, where they bump into their neighbors, to jump either this barrier, which undoes my product, or this barrier, which converts my ion pair into the 1,4. Because what I want is to get as large a yield as possible of the 1,2 compound. And the longer I leave my system reacting, the greater the chances of the odd molecule jumping this barrier to unfold my product, or that barrier to give me the 1,4. So I want low temperature, so I will allow this reaction to occur at the expense of the others, and I want short exposure to prevent the ionization of this species and the collapse of the ion pair to give the 1,4 product. So to get the 1,2 species, I want low temperature, short exposure to get me 1,2. Fine. What if I wanted the 1,4 product? How would I engineer my reaction to get a preponderance of the 1,4 compound? And as you might guess, what I will need to do is to do just the opposite. I will need to run the reaction at a high temperature for a long exposure. High temperature for a long exposure. In other words, long time. And that's going to give me a preponderance of the 1,4 product. Well, let's see how that works. Regardless of the temperature at which I run this reaction, the fastest step is always going to be the formation of the 1,2. So my ion pair will always be forming the 1,2 product very rapidly. But if I use a high temperature, I now have access not just to this pathway, I now have real access to this pathway, and I have access to that pathway. Right? I have enough energy in the system to carry all out. Now, this will still be the fastest step. This is still the fastest step. But pretty much almost as quickly as this forms, well, not as quickly, but this will form quickly. But I have enough energy in the system for the 1,2 product basically to ionize and reform my ion pair. And once my ion pair is made, I'm going to have enough energy in the system to climb the tallest hill, which is the one leading to the 1,4 product, and fall down. But here's the kicker. While I can do this, right, which is going from the 1,2 to the the ion pair to the 1,2, and I can go from the 1,2 back into the ion pair, and I can go from the ion pair into the 1,4, there is a precipitous drop from this transition state to the 1,4 product because it's so stable, right? The transition state is high because this represents the larger activation energy barrier, right? Because attack at the carbon number 4 is more difficult. The product is very stable because the alkene is disubstituted. So there is a huge drop from here to here, which means the activation energy barrier for the 1,4 product to unfold into the 1,2 product is high. I'm doing the reaction at a high temperature, but not a crazy high temperature. So I don't really have enough energy in the system, by and large, for the 1,4 compound to unfold into the 1,2. So pretty much whatever 1,4s generate, whatever species, whichever ions react, climb the barrier and fall into the 1,4, they're stuck. Right? They're in a deep energy well, and it is very difficult for them to come out. Now, will any come out? Absolutely. You'll probably get one in every couple thousand molecules having enough energy for the 1,2 species, the 1,4 species to ionize and regenerate the ion pair. But it's not going to be a lot. So what I want to do is to run my reaction at a high temperature, which gives me access to this pathway, right? Which gives me access to that pathway, and also really gives me access to this pathway. Because I know I'll be making the 1,2 product the fastest. Fine, I'm going to accept that. I want to give the 1,2 species enough energy to jump back over the barrier and give me the ion pair, because once it's the ion pair, it's fair game. Right? The ion pair has two options: make 1,2 or make 1,4. And the longer time I leave it, the more the 1,4 product will simply accumulate. Right? From the ion pair initially forming into the 1,4, and then from some of the 1,2s reionizing, and then some of those forming the 1,4. So to get the 1,4 product, I'm going to run my reaction at a high temperature and for a long exposure. The question students always ask is, what do I mean by a high temperature? What do I mean by long exposure? And unlike the SN1, SN2, E1, E2 discussion where we can say, well, 50 degrees is considered high, there isn't a simple answer for these ionic reactions. It really depends upon the particular reagents. And usually when you get questions of this nature, they will give you a comparison. And they'll say, well, what will I get if I ran the reaction at 50 degrees for half an hour? Well, that's low temperature, short exposure. How would that differ if I ran the reaction at 150 degrees for 5 hours? Well, clearly that is a high temperature and a long exposure. So you should be able to tell from the context of the question what we mean by high temperatures and long exposures. Okay, so that would be the polar addition to dienes. The other reaction of dienes that we're interested in is a reaction called the Diels-Alder reaction. It is the Diels-Alder reaction. And the Diels-Alder reaction turns out to be one of the most important reactions in organic chemistry. And in a very simplistic view, the Diels-Alder takes a diene, right? For example, I'm using 1,3-butadiene. It takes a species called a dienophile. So I've drawn here an alkene. We'll see later on it doesn't have to be an alkene. It's called a dienophile. And in the presence of heat, what I get is the following. Okay? And the reaction goes via an intermediate, a transition state, which looks like this. So what I've done is 1, 2, 3, 4 carbons are here. 1, 2, 3, 4. These 2 carbons are here. And this looks like a 6-membered ring, and I have in this 6-membered ring 2, 4, 6 pi electrons. So it's almost an aromatic type of feature for this transition state. The species eventually forms a carbon-carbon bond at the expense of the carbon-pi bond. So I form a sigma bond at the expense of a pi bond. In other words, in a sense, what is happening is this. Right? I form this sigma bond at the expense of that pi bond. I use this pi pair to form that sigma bond, and I use this pi pair to form that sigma bond. And the final product of the reaction turns out to be a cyclohexene. The final product of the reaction is a cyclohexene. So why is this reaction so important? And it is important really for 2 reasons. Remember, we keep harping on the value of reactions in which we make and break carbon-carbon bonds. Well, in this reaction, we are making 2 carbon-carbon bonds simultaneously. So it's of value simply because it's a reaction in which we make a carbon-carbon bond. It is of particular value because it involves tandem formation of 2 carbon-carbon bonds. And the other really important feature of the reaction is I am taking acyclic precursors, as I've drawn this, and I'm making a cyclic species. So I'm taking a diene and a dienophile, and I'm generating from them a cyclohexene. So I'm going from 2 acyclic precursors, and I'm generating in their stead a cyclic entity. Now, it's not just any old cyclic entity, it is a 6-membered ring. And 6-membered rings are of particular value when it comes to generating molecules that are bioactive or compounds that are sort of natural products, because a lot of rings that occur in living systems are actually 6-membered rings. But this is not just a 6-membered ring. It's a 6-membered ring that has what we call retained functionality. Because I have a carbon-carbon double bond in my 6-membered ring. So I can direct chemistry. I can do chemistry at particular sites. I can do chemistry at vanillic carbon. For example, I can add bromine. Or I can hydrate, or I can hydroxylate the alkene. Or I can choose to do chemistry at the allylic position, using allylic bromination. So I can target where in this molecule chemistry happens. So it's not as if I simply made a cyclohexane and then all bets are off because I've got to use free radical chemistry. But I'm using cyclohexene that allows me to do functionalizations in particular positions in the molecule. So the Diels-Alder reaction then is useful because it involves 1, tandem formation, in other words, simultaneous formation, of 2 carbon-carbon sigma bonds. That's a big deal. It allows us to go from acyclic precursors, right, from acyclic precursors into a cyclic species. I'd also say cyclohexene, right? So it's cyclic, but the fact that it's a cyclohexyl species means it has value because it allows us to synthesize natural products, so value in natural products, and also because it's an alkene, it has retained functionality. Okay, so Diels-Alder reaction is a very, very important reaction. Okay, great. What are the features of the Diels-Alder reaction? It turns out the Diels-Alder reaction has some features that are of particular importance. 1, the reaction is highly stereospecific. Okay? And I'll explain what that means as we go along. 2, electron releasing groups in the diene and electron withdrawing groups in the dienophile facilitate the reaction. Okay? So what does it mean when we say the reaction is highly stereospecific? Well, what it means is that, for example, if I take my butadiene and I react it with a trans alkene, let's say a cis alkene first, my product will be, now I recognize this is Diels-Alder, and so I'm just going to go ahead and draw a cyclohexene, because the product of a Diels-Alder reaction is a cyclohexene. The double bond of the cyclohexene will be couched in what used to be the diene unit, right? So again, these 4 carbons are here, right? 1, 2, 3, 4. And my pi bond is going to be formed between these 2 carbons, which were here, right? Between these 2 carbons. So basically what I've done is I've made a 6-membered ring, and the lone double bond in the molecule, the lone pi bond, is going to be nestled in what used to be the diene unit. This carbon and that carbon are going to be here and here. Now, because my precursor, because my dienophile was cis, it means that the methyl groups in the product will also be cis. That's what we mean by being stereospecific. Stereospecific means that a particular stereoisomer, in this case the cis species, gives rise to a particular stereoisomer, in this case the cis species. Cis gives cis. Now I want you to realize that this molecule has a plane of symmetry, which means it's achiral. Therefore this entity and its mirror image, which would be this compound, right, are equivalent. And by the way, I got this mirror image basically by imagining that there's a mirror plane behind the screen. And this is what would be reflected. Okay, I could have just as easily drawn the mirror image like this, right? I could have drawn the mirror image like this by imagining a mirror placed somewhere here, right? There's a mirror somewhere here. So, in any event, the molecule has a plane of symmetry, it has a sigma, and therefore the molecule is achiral. But in this reaction, cis gives cis. Cis and only cis gives cis and only cis. That is stereospecificity. Well, what if I had a trans species? Good grief. Well, if I take, get a bit more room here. If I take the alkene, my diene again, and I treat it this time with a trans alkene, what do I get? And the answer is, well, look, I recognize this is Diels-Alder. Therefore, whatever else I know, this reaction has to give rise to cyclohexene. So I'm going to draw my cyclohexene. Well, again, carbons 1, 2, 3, 4 are here. 1, 2, 3, 4. And these two carbons are going to be here. Let's make these with an X. Those are going to be here. But the groups on these carbons are trans. The groups on this alkene are trans, and so they'll be trans in the product. Now, this shows stereospecificity. Trans and only trans gives rise to trans and only trans. The only issue is there are actually two different transes, because this molecule has no mirror plane. Therefore, this molecule is chiral. And that means the mirror image of this species, which happens to be this one, and it are not going to be superposable. So I'm going to make two transes. One will be plus rotatory, one will be minus rotatory. Right? So in other words, I'm going to make the DL pair of these dimethyl cyclohexenes. But fundamentally, the reaction is stereospecific in that the cis gives the cis, the trans gives the trans. It just turns out that there's one cis, aka the meso, and there are two transes, right, aka the plus-minus pair or the DL pair. And again, we don't know a priori which one rotates plane chloride clockwise, which one rotates it anti-clockwise. That's something you have to determine experimentally. There is so the reaction is highly stereospecific. There's a point that I sort of neglected to mention, which I should do now, and that is, if you notice, I keep drawing my diene this way. But in reality, you know, this is a sigma bond about which I can have free rotation. So I can rotate that diene to look like this, right? Those are different conformations of the diene. In fact, the conformer on the right is actually the more stable conformer because it places these groups in an anti-fashion, right? The groups are further apart from each other. So what do we call these conformations? Now, if we were doing, if, for example, I was simply looking at, say, bromine, disubstituted bromine, here and here, I would call this species the syn conformer. This would be the anti-conformer. And in a sense, I can still do this with the dienes, but what is commonly referred to, is this is called the S-cis conformer. This is called the S-trans conformer. And the S stands for pseudo, even though pseudo begins with a P. But that's just neither here nor there. So it's called pseudo-cis because it kind of looks as if it was cis. Now, technically, it should be called syn. But by convention, it's developed in the name pseudo-cis or S-cis. And similarly, this is called the S-trans conformer or pseudo-trans. Really, I should have called it anti, but that's just the lingo for Diels-Alder. What is important is, even though the diene is able to rotate from one conformer to the other, the only conformation in which the diene is Diels-Alder active is when it is in the S-cis conformation. Right? Let me say it again. The only conformation in which a diene is Diels-Alder active is when it is in the S-cis conformation. That has an impact on, it has a minimal impact on acyclic molecules, because acyclic species can rotate, and there's rotation about the single bond billions of times per second. Not a problem. The problem arises when the molecule is cyclic. So for example, if I look at this molecule, this isomer is Diels-Alder active, right? Because I've got my diene, not a problem, and it's in the S-cis conformation. On the other hand, this isomer of this ring system is Diels-Alder inactive, because even though it is a diene, the diene is in the S-trans conformation, and it cannot get out of it, because the bridged ring system is locked, and I cannot rotate the system out of it. So this is a diene, but it's Diels-Alder inactive, Diels-Alder inert. This is a diene, but it's Diels-Alder active because it is in the S-cis conformation. Alright, so we were describing some of the features of the Diels-Alder reaction. And one was the reaction is highly stereospecific. The other is that electron releasing groups in the diene and electron withdrawing groups in the dienophile facilitate the reaction. Okay, first of all, let's explain what we mean by ERGs, electron releasing groups, and EWGs, electron withdrawing groups. So ERGs are electron releasing groups, EWGs are electron withdrawing groups. And let's explain what those mean. And you sort of met a couple of these in the past, and we discussed this and then we stop this lecture. So, groups can be electron releasing for one of two reasons. They can either, or by two mechanisms, let's put it that way. They can be electron releasing by induction or by resonance. Right? So, for example, I can have a group that is an ERG by induction or by resonance, and a group that's an EWG, electron withdrawing group, by induction or by resonance. What kind of groups are inductively electron releasing? And the answer, you've met those are alkyl groups. So methyl, ethyl, propyl, the various types, and so on, butyl, the various types. These are all electron releasing groups. And we've seen this before. We know, for example, tertiary carbocations are more stable than secondary, more stable than primary. And why is that? Because alkyl groups are electron releasing. The more of them I have, the more they stabilize the system. We know that if I look at alkenes, tetra-substituted alkenes are more stable than tri-substituted alkenes, which are more stable than the dides and the monos and so on. Why is that? Because the vinylic side is electron poor. And the more R groups I have on them, the more they dump electron density in, the more I feed it, the more I stabilize it. So alkyl groups we've known from Chem from 301 are electron releasing groups. What groups are electron releasing by resonance? And the answer is, I simply need to have an atom X that has a lone pair of electrons. And the atom X should either be nitrogen, oxygen, well, typically nitrogen and oxygen are the electron releasing groups. So, for example, I can look at OH, or OR, or NH2, or NR2, and so on. Those are electron releasing groups by resonance. Now, exactly how is that accomplished? Well, let's see. Suppose I have this species, right? I've got a vinyl alkyl ether. Well, the lone pair of electrons on that O will be in resonance with the pi bond, and what we'll end up getting is a system that looks like this. And what I have in essence done by resonance is I have dumped electrons from the O into the pi system, into the double bond, which is why this end of the molecule now acquires a delta negative charge. And to show that the O has dumped electron density into the pi system, it's now depleted of electron density, so that's a positive charge. And the atoms usually are limited to O and N because since we're doing organic chemistry, the atom they're bound to is carbon. And, you know, carbon has p orbitals of a certain size. Whatever atom I put here has to have p orbitals that are also of a similar size. And for that to happen, they have to be complementary. And the only atoms that fit that bill are the heteroatoms in the same period with carbon, which are nitrogen, oxygen, and fluorine. Now, we're going to cross fluorine off our list because fluorine has such a huge electronegativity that fluorine ends up being an electron withdrawing group. It does so by induction. So my ERGs can function either by induction, and those are alkyl groups, tried and true, or by resonance, and those are groups that specifically have O or N bound to them, and the O, N have their lone pairs of electrons intact. Electron withdrawing groups can function by induction, and those would include my halogens, chlorine, bromine, iodine, fluorine. It will also include any species with a positive charge. So for example, if I had NH4 plus or something of that nature, that would be an electron withdrawing group. And that's fairly obvious. If it's positively charged, it's going to suck electrons towards it. I can be an EWG, electron withdrawing group, by resonance. And for that to work, I need to have X multiply bound, double or single, to Y, such that there is a difference of electronegativity between X and Y. So it couldn't be a carbon-carbon double bond or triple bond, but it could be a carbonyl, it could be iminyl, it could be nitrile, it could be sulfonyl, and so on and so on and so on. So any one of these turns out to be an electron withdrawing group by resonance. And why is that? If I take my carbon-carbon double bond and I put a carbonyl next to it, what do I have? The answer is, well, for all carbonyls, we can draw a resonance form in which the minus charge is on the O, right? And importantly, the positive charge is on the carbon. And we've used this argument at length to account for why carbonyl compounds are such wonderful electrifiers. But if I can draw this resonance form, it means I can now draw this resonance form. And in that resonance form, what I have succeeded in doing is bleeding electron density from what was once the carbon-carbon double bond. So if I attach X double bond Y to a carbon-carbon double bond or triple bond, I will bleed electron density from this bond by resonance. So carbonyls, nitrosyls, nitro, all of that lot, sulfonyls, are all electron-releasing groups by resonance. And I want you to remember, resonance is a more potent force than induction. Okay, resonance is a more potent force than induction. So we now know, therefore, that if I have ERGs on my diene, and these can be ERGs, the diene is activated. EWGs in a dienophile activates the dienophile. So, for example, if I ask you which of these dienes is most Diels-Alder active, okay, what you would tell me is the most Diels-Alder active one is this one, right? Number 3. It is the most active because my diene has a group that can dump electron density into it by resonance. This one is second because this diene has 2 alkyl groups on it that can dump electron density into it by induction. This is third because this has no groups that can dump electron density into it. If I gave you a dienophile, right, this one, and this one, and this one, and I ask you which one is the most Diels-Alder active, the answer would be this one. Because this one is able to dump electron density by resonance. This will not dump, but the cyano group will draw electron density from the carbon-carbon triple bond by resonance. This will do it by induction, the fluorine, this will be second, and this has no electron withdrawing group, so this will be third. Okay? So we stop here and continue at the next lecture.